Good evening, everyone. So my name is Susmit, and this is going to be a lecture series on Statistical Mechanics. And I'm glad that Ensemble gave us opportunity to get in this series. So why do we need Statistical Mechanics? So what do we know in that? So there is for any system we have, there is a microscopic. There is a macroscopic tension. So, when we talk about the microscopic picture, so you can think, for example, a gas is a system of particles which are interacting with each other. And so, to describe the state of in a microscopic way, state of the system in a microscopic way, you would need to specify certain parameters. So for that, you describe something called a microstate. So if you take the example of a gas, you can classify the position and generalize momenta of the system. And if you label all the positions and momenta of all the atoms in the system, you can get the state of the system. Now in the macroscopic perspective, you have a macro state. Wherein you specify the thermodynamic properties of the system. So you can have properties like energy, internal energy of the system, which is like the total energy in the system. You can have properties like the volume, the number of particles, pressure, temperature, and also space. So different systems have different kinds of microstates, and so you can represent them by a generalized position and momenta. And this is in a classical picture. So I can give you an example of a system such as spins. You can have a state of many spins, and if you give the orientation of each spin of the system, you get the microstate of the spin system. Similarly, for the you would want a macrostate corresponding to this. So you would know an interaction between the spins, and there never be total energy of the system. There can be magnetization because it's aligned to each other, and so on. So yes, so you have a microstate in the microscopic description, you have a macrostate in the macroscopic description. So what laws does this microstate follow? So how does it evolve in time? So that is given by in classical mechanics, it is given by the Hamilton synthesis equation, which is so you construct the Hamiltonian of the system, and this Hamiltonian is a function of all the generalized coordinates and momenta of the system, and these equations give you the dynamics of the system. Similarly, for the macrostates, you have the laws of thermodynamics. So they are the first law, which states that there is a statement of energy conservation basically. It states that dU is equal to d given the system as we go about the dynamic system, which is equal to ds and e. So yeah, and you have the second law of the system, which says that in an isolated system, any process which occurs in an isolated system will give entropy change greater than 0. So your entropy will always increase in any process in an isolated system. So this is a microscopic description and this is a macroscopic description. What statistical mechanics does is be a bridge between these two. So, and use law of probability. So, you use laws of probability to go from this microscopic picture of the system to the macroscopic picture of the system, and and that is what statistical mechanics does. So, and why can you use laws of probability? You have a large number of degrees of freedom of the system. So, usually your system has numbers of the order of the Avogadro number. So, you have a large number of particles in the system. So, you have a large number of degrees in the system. So, you can use statistical methods to possibly go from a microscopic description to a macroscopic description and get these properties from these properties. And so, why this is necessary? So, one thing is, if you see the microscopic description of the system, there are Hamilton's equations for each Qi and Pi. So, this is, suppose there are n particles. So, there are clear equations for momentum, for Qi, let's say, and clear equations for other positions.
Is it because of the
Yes. So, if you consider each particle to have the freedom values. So, you have these many equations for tension and momentum. And you see, n is such a large number, solving these many equations is practically impossible. And one more thing is, these equations are very chaotic. So when you solve a system of 6 and differential equations, you will need 6 and so these are all first order. You will need 6 and initial conditions. And if you are able to solve the equations of motion, you will get Ui as a function of time and Pi as a function of time. But what you can see is that these kind of systems are very dependent on the initial condition. So if you make a small change in the initial condition, you will get widely drastic, very different Ui and Pi at a time. So your Ui and Pi exponentially varies. This is called chaos. So it is not necessary to solve these many equations just for getting the wrong final thing. So you would not want to do it. So to go from microscopic to macroscopic, we need this step. This bridge of statistical mechanics. So before that, I would like to give some probability triangle. Because we are using the laws of probability. So for this, you need a bigger count. You want to know how to count the different states or something like that. So we use the fundamental principle of this states that if you have A ways to do a task and B ways to do a task B, and these two are independent tasks, then you have A times B ways to accomplish task A and task B. So this is, you can say, the multiplication rule and fundamental principle of counting. Then I assume all of you know little bit combinations of relationships. So I'm just laying down the formula. So number of ways of choosing n1 objects out of n objects on distinct objects is called NCN. NCN1, which is n factorial by n1. Now suppose there are R boxes, and we want to distribute n objects in these R boxes and distinct objects. These R boxes, such that n1 go to the first box, n2 go to the second box, on to NR goes to NR objects go to the R box. The number of ways of doing this is n1. So you choosing n objects out of the n1 objects out of the n, and using in the first box. Out of the remaining objects, remaining n minus n1 objects, which is n2 and this is in the second box. So on till n minus n minus.
So, generally, this method is repetitive, doesn't it?
What kind of repetition?
Extra number.
Yeah. Okay. So boxes are labeled by. And when you expand this, you will get this. And you should know that come over and this is basically comes. So this is called a multinomial coefficient. Yeah, and this is the number of really distributed numbers. Okay, so these are the things that we need from counting. Now let's see what problem we need. So for this, we define a sample space. This is the set of all outcomes of an experiment. Outcomes of a random. you do some experiment and you see your outcome to be something, and you will have many possible outcomes. The set of all these outcomes are reducing omega set. Then you have the set of events. This is a collection of events which we want to compute. So what is an event? Event is a set consisting of certain number of outcomes of the experiment. So this set of outcomes of the experiment. Then we define something called a probability function, which maps, which takes values from the set of events, the collection of events, and it maps into this interval in the real line. So every event is assigned some number in this interval from 0 to 1, and the number assigned is called the probability of that event. And you can have an event without any outcome, which contains no outcome, and probability of that event is 0. And you can have an event with all outcomes, and the probability of that outcome is so for an example, if you consider the experiment of coin toss, you see that the sacrifice contains of which the heads are tails, and you can assign a probability. You can take a event to the head. You can assign probability half to, or you can assign probability this half, and yeah. So this is an example. Now let's see. So there's something called conditional probability. So sometimes you have an event A occurring, and if you have another event B occurring, the value of the probability of the event B occurring can depend on what outcome was of the event A occurring. So that is denoted by this. This is the conditional probability of B occurring given that A occurs. So this is the probability. And this is defined by this. So you have an event A, and there are some there is some overlap between the events A and B, and the ratio of those the probability of the overlap divided probability of A gives the probability that B occurs, given that A occurs. Now we define something called independent reason. It says that probability of occurrence of A intersection B is the probability of A times probability of B. And why do we call these independent? Because here we have A equal to B. We have so the conditional probability that A occurs given that B occurs is same as the probability that A occurs. So the occurrence of A does not depend on occurrence of B. That's why we call them independent variables. And similarly, we have B given A is equal to B. So using this relation, you can there's something called the multiplication rule. It says that probability of A and B both occurring together equal to the probability that A occurs times the probability that B occurs given that A occurs. And this is also equal to the probability that B occurs times the probability that A occurs given that B occurs. So this is called the multiplication rule. Yeah. So now we define something called random variables. So what a random variable is, it is a function. I'm denoting the random variable as x. It is a function which takes value from the sample space and goes through the calculates values in the real time. So every outcome in the sample space is mapped to a value in the real world. And to associate the probability distribution of the random variable. The probability that the random variable takes the value x is the probability that the random variable x takes the value x is the probability that an outcome omega, which belongs to sigma, is the probability of that outcome omega, such that this x of that outcome omega is the value x. So whatever outcome x was taken from whatever outcome omega that x was taken from the sample space to R, the probability of that outcome is the probability that x is equal to x. So you can have two types of random variables. What happens in this is the random variable x takes discrete values, which means it takes counted values in the real number line. And you can define, you can call them xi and you can label them by indices. because they are countable. And some of our properties of the vector is equal to 1. And so we call the probability distribution X of x is the probability that x is x. So this is the probability distribution of the random variable xi, and we define it this way. And this is the normalizing condition that says that the sum of probabilities of all the possible values x can take is 1. So for our example of network case, we can define a random variable which is 1 and is u. And for this you can write the probability distribution as Px of 1 is equal to half. Yes. So when it is flipped up and it says the second type of random variable you can have is a continuous random variable. This is what happens is x can be continuous values over the line. So you can define a probability distribution for this continuous random variable also. So you call that a probability density. Denoted by this. This is the probability density. Why this is the probability density? Because this value of fx times dx gives the probability that the random variable x lies in the range x and x is dx. So you can see that fx of x is a probability density because this density times dx is the actual probability.
One formation, when you create the probability that x lies in x and x of dx, is it open or closed sequence?
Doesn't matter. Doesn't matter very much.
It's open, but it doesn't matter.
Yeah. Because
Equilibrium integral is the equal to.
yeah, so you want singular. So when you are in a continuous domain, the probability that you get a single value of x is 0. So it doesn't matter. And this also follows the normalizing condition, where you have the sum in replace here the integral. I'm assuming x goes from minus infinity to plus infinity, and this will be equal to 1. So this is the normalizing condition for the figures. Yeah, in physics, it was nice. I'm kind of doing this in a very non-rigorous way because we are doing physics. And you will have a course on probability next semester. Next thing we do is logically distributed and then so let's say there are two random variables x and y. Define a joint probability distribution of both x and y. By this x, y. This gives the probability that x lies in x and x is in this range, and y lies in y and y in this. So this times dx. This times dx dy gives the probability that x lies in x plus dx and y lies in y plus dy. And this is called the joint probability distribution of the random variables x and y. And we will have a normalizing condition here also, and that would be a double-edged figure. Now, given this joint probability distribution, you might ask, what is the probability distribution of x and y individually? So, to find that, we will use something called the marginal distribution. So, you have this probability distribution of x and y. You will integrate out over y. So you will basically sum of sum the probability over all possible values of y, and then you get the probability individually, and that's what we call the joint the marginal distribution function. The marginal distribution function of x is by so this times dx gives the probability that x lies between x and x plus dx independent of y. So because you have already integrated out, and this is an important thing because we will be using this a lot of time to understand. Similarly, for y, you would have this. And you call two and the variables x and y independent. Okay. So this is the definition for independence of two random variables. Basically, the joint distribution function separates into a product of the marginal distribution function. And let's see some common probability distributions. So it's called the Gaussian distribution, or also called the normal distribution. And its probability density function is and its probability distribution function is this. Unknown distribution is the exponential distribution. And this is for x going from and this term in the front is the normalizing factor. Doing the integral, if you do the integral, you will get this is the normalizing.
What do sigma and mu stand for?
Okay, yeah. So sigma is called the variance, and mu is called the mean. And I'll define these quantities very well. I forgot the normalization. So you have and this is for x greater than equal to 0. So this is an exponential and also, and mostly we will use these two. So let's define something called the expectation value and variance. So we define expectation value of the random variable x as this. So this is called the expectation value of the random variable x, and this gives you a kind of, and that affects the probability distribution of x, and this kind of gives you the mean value of. Similarly, you can define expectation something called the moment, nth moment. So this is x bar n times n. So this is like performing an expectation of x, and then you can define something called the variance. This is expectation of and this you can show it to be as and mu is the expectation value. So this is something called the variance, and it's not a value. Now what you do, and you can define ranks of variance. You see that variance will always be a positive quantity because this is a square and your equilibrium over the square is, and your probability distribution function is always positive. So you can define the square root of variance and this. So here sigma was the standard. Sigma was the standard deviation. Mu was the expectation value of x. So mean of the distribution. So if you take the distribution and you run it in this formula, you will get mu. And if you run it in this one, you will get sigma. and you can try that.
Yeah. What do you mean by anything?
Similar approach. So, you multiply the probability distribution by x squared, and then you integrate over x.
Like the expectation value is analogous to mean value. What is the moment analogous?
What?
Like, what does the moment tell us? The expectation value gives the mean. What does the moment give us?
Okay, so the square x square moment is kind of tells you about how distributed the distribution is about the loop. So more if your distribution is more wide, you will have a larger value of this variance, and if your distribution is narrow, you will have a small value of this variance. And higher moments gives you, so if you have a probability distribution like this, which kind of is the variance, this middle part is the mean, and if your distribution is skewed towards one side, something like this, or if it is skewed towards the left, those skewness would be given by the higher limits. So x cube moment gives the skewness and
Since we have explicitly defined the x to the power n as moment, does it have some special?
yeah, it is used in many situations, such as like when you are defining correlations. That time, the nth order correlation between the variables would be this is enough of probability for that. So let's get back to the stat method. So what you are essentially doing in stat method is construct a habit domain. And this construction is dependent on a model. So you model your system as a certain thing. You would probably define different positions and momenta, and you see how they interact, and you construct a Hamiltonian for that system. Now, once you have this Hamiltonian, you apply the statistical methods. And then you get some properties of it. These properties, if they match experimentally with the experimentally seen properties, you have a good model. And if they don't, you would need to change your model or see if these methods are valid. So since we defined the Hamiltonian, we can, instead of the generalized coordinates area, you can define something called a phase space. So the phase space is like the space where space of all these generalized momenta and position together. So you can say Pi and Qi. So if you have an ideal gas, for example, you will have a 6 and 9 dimensional space. And each point in the phase space corresponds to one set of Pi and Qi. Now your system at a given instant of time has a single set of Pi and Qi. So your system at a given instant of time is a point in the phase space. This right? So, and in time, you will see your Pi and Qi changing by the Hamilton's inverse of motion. So your Pi and Qi are changing. And this point will be basically going as a trajectory in the phase space. Now, since there are this huge number of degrees of freedom of the system, it can be assumed that in a long time, this system explores the whole phase space, which whole space space is accessible to it. So, because of the randomness of the system, because of this huge number of degrees of freedom, the system would explore the whole phase space given a long enough amount of time. And this randomness is not in the microscopic equations of motion. It just arises because you have this large number of degrees of freedom, and you have many possibilities to go and so basically this point explores the whole phase space.
Wouldn't having more degrees of freedom be counterintuitive to exploring the entire system?
Right. But since you have these large number of degrees of freedom, you have many motions possible, and due to that, even long enough time, you need a long enough time, and after that, your system basically explores the phase.
So, like, we are giving infinite time to in two cases. One is less degrees of freedom, one is more degrees of freedom. Even though it's infinite time, which one would get that different?
So, if you have less degrees of freedom, your motion is kind of it can be kind of constant. So, when you have, suppose, you have Earth and you have an object, and the object is falling towards Earth, it is just going through this path. It is not exploring everything else. But when you have this large number of degrees of freedom, it will tend to explore most of it.
This is that follows the half of half. If by absolutely reading that follows then I have not zero problem.
Okay, so
What do you mean by?
right. So if you have a system whose energy is fixed, the system can only access those PIs and QIs for which the total energy is. So those PIs and QIs apply.
There is potential.
There can be.
What if there is
Then let's go to another.
What is the response to one particular
Yes, yes.
information about one molecule?
No. So one,
Get the information about all them.
all of them. You can, for example, construct a phase space for each particle also. That will be a six-dimensional phase space of moment and dimension of all the data.
When we think of it's an initial point of inner space, and we know that the transformation that the point we take is canonical. So how can we say that it will improve the whole thing?
Okay, so I told you once that it's pure field, right? So if you displace this thing little bit, it will take a very different trajectory. So this small fluctuation can cause a widely different trajectory, and then you have this mixing up and waste and whatever it is.
So what is more important in exploring the whole chaos or the more number of degrees of freedom?
Both of them. Because of the more number of degrees of freedom you have.
We have chaos.
So we can take a microstate PID here and a small volume around it. The probability that, so we can assign a probability that the system is in this volume around this microstate by the following. So you can take a long time. Let's call it probability of. So you take a long time. You see the amount of time the system spends in this region of the microstate. Divide that by the total time in E. And the fraction it spends in this is the probability that the system is in this. So you can assign a probability of the system being in this microstate.
What is will be here?
Delta T is the time that the system spends in the time the system spends in this region of the phase space in the total time T observed. Now you see that any macroscopic quantity, because I call it as a point. So your O can be, for example, energy or some variable which depends on the microstate of the system. When we measure this quantity, what we do is basically take a time average. That what I mean is, so when you have the motion of the microstate, this is very fast. So your microstate changes rapidly from one state to another. And for example, you can see in ideal gases or gaseous systems, the velocities are of the order of 10 to the power 5 meters per second. So your microstates change very rapidly. And when you do a measurement of, suppose, energy or pressure, what you are actually seeing is the average value over a long time. So your measurement will probably be over 1 second, and and the system is changing in 10 to the power minus 5 meters. And so the system is exploring many phase points in this 1 second time period. And you would see an average value of the measurable quantity is that. So the measurements which you do is basically taking a time average. And by time average, what I mean is this. So over time, your quantity changes, and you measure your quantity over the time from 0 to t, and the average value is what your measurement divided into 0. Yes.
And also, you find that really there was already one that really compared with that. So are you adding the probability also?
Yeah, it's the total. So this delta t is the total time the particle spends in that.
You want any particular instance?
No, it can be like for some time it spends and then again comes back. So this is what I call the time average. Now we define something called an ensemble. Out of the ensemble. So what an ensemble is basically you have a system. And you take like a large number of copies of the same system, and say that the total number of copies is 10. You take a large number of copies of the system, and each of them are not they are not in the same initial condition. So they're basically different microstates, but the same macrostate all of them. So when you plot each of their points in the phase space, you will get the distribution of points. And then you can take the number of, so this is an idealized construction, constructed in a mind. So you can take the n to the infinity, and then you will have a large number of points moving around in the phase space. Then you can concentrate on one particular point, take a volume around it, and you find the density of the number of points in this. So I denote that by rho p. So you find the density of the number of representative points of these microstates of each of the system in the ensemble. In this region, the density I'm calling is this, and this density is like the probability that the system is in this order. Is this fine?
So the point that you are marking are all the phase states accessed by each system.
No, this is at a given instant of time. Each point represents one system. So you have a large number of systems, and all these points are one. So
earlier we said that if the entire phase space will be accessed. Here the number of systems are infinite might multiply the entire phase space.
it is kind of nice. It is similar to that. So what I'm trying to say here is what happens for a single system in a long time is equivalent to this multiple systems at a single instant of time. So, yeah. So you assign this density to every point in the phase space, and then so the assumption in statistical mechanics is this way of time average. And so you can do an so any observation all these. Let's denote time average by y. And now you have the density of points in the phase space for this ensemble approach. Now you take any point O of P2 and I'm calling this an ensemble average. You can multiply So you can assign an ensemble average to any quantity of P2. So you will have this system will have one of P2, this will have one of P2, and so on. And you multiply the having the value of P2 times the density at this point, then you integrate over the whole phase space. This would give you an average value, right? So this is what I call the ensemble average. So what we have now is two ways of calculating averages. One is to the time average, and one is to the ensemble average. And due to this system being very large and complex, I'm saying that this is an assumption. I'm saying that what this single system faces in time is equivalent to the points all of these systems have at a single instant of time. So basically what I'm trying to say is this act of time averaging is same as act of ensemble average. So and the systems in which your system explores the phase space in the complete phase space. These systems are called ergodic systems, and yeah, so this is kind of the ergodic hardware. So this density of points in the phase space can change in time also. Right? You call the system stationary if this does not explicitly depend on time. The rho PQ does not explicitly depend on time. And if this is true, then your all these average ensemble average values don't go to that. And when these average quantities don't change in time, this is what we call as equilibrium. So stationary ensemble is a good candidate for equilibrium. Now, our system follows the Hamiltonian diagram, so we can write it. Now, consider a volume in the phase space. And let's call the what the
what equilibrium systems is right. This is different. The previous statement that the time average and the instantaneous moment average is the same. Because a non-equilibrium system, this will change. But why will the time average change?
The time average won't change. So time average
that is only true for an equilibrium system.
Yeah, you can say an ergodic system. In non-equilibrium system typically does not explore the whole phase space. So let us consider volume in the phase space, and let us take the volume omega. So there will be some amount of points in the phase space. So the total number of points, so the rate at which the number of points change inside the phase space is this is the number of points in the phase space. The rate at which it changes this. And since we have already constructed an ensemble, there can't be generation of any new points or deletion of any new points. The total number of points are conserved. And so the number of points in the system can change only by throwing of points also. And so how do we find how many points are going outside per unit time? So for that, we define a flux. This is the velocity in the fixed and dimensional phase space, defined by del y. So this vector has fixed and components. First PNR the Dy dots, and second PNR the Pi dots, and this rho times the V gives the flux. It gives you the rate of flow per unit area. Take another one. Is this vector of Ui dot and Pi dot. So what I'm trying to say is rho V dot n cap, wherein n cap is a normal vector to an area. This is times the area. Times the area gives the amount of particles flowing through the system per unit time. So how do you find the total number of points flowing out of this volume per unit time? For that, you integrate over this surface. For the surface sigma. So this is the total number of points, representative points, flowing out of this volume per unit time. What? Yeah. And the dimension of the surface is one dimension. How?
How do you define the what product?
Define the
What product?
dot product. Okay, so this is a 6-dimensional vector and an object dimension. And is also a vector. What? So the number of points as a whole is conserved. So the number of points coming out of the system per unit time is equal to the change in the number of points inside the volume. So you can equate these two things, and you can write So this n is the outward vector. So this would represent the outward flux, and an outward flux would decrease the number of particles in the system. So there is a negative sign here. Now, do you all know the Gauss theorem? So from this, you can write this as divergence of rho v and right. And what is this divergence? This is 6-dimensional divergence. So what that what I mean is this line. So you have each of these are components of the vector only, and this is the corresponding coordinate and the right. So you can take this thing this side now, and amplitude derivative inside, and right derivative.
Susmit, while you are writing the derivative outside the integral, will it be the total derivative?
Yeah, you can say, but rho doesn't.
That's right. Once you take it inside, then it should be partial.
Yeah, you can say.
Why should the integral be total when we are writing a calculation? Why should the integral be total when we are writing a calculation?
Because this thing does not depend on anything else. It does not depend on Q or Q. It's just a single, it depends only on Q.
Once you have integrated out, all those variables are not dependent.
In this, so inside, so the change in omega is just the change in number of representative points is the change in density inside is just due to the explicit time dependence. It won't depend on the independent simplicity, which is coming to Pi and Qi. So Pi and Qi is still contributing the flux, and the explicit time dependence is
What are the variables that inside it? And why do we
rho is a function of Pi and Qi and P. Now this is true for any volume in the phase. So you can say this term goes to zero because you need this will do in any volume. So you can say this. And you can expand this as now you can use the product rule and expand this and then go then one and Pi dot. Then no time delay Qi. And this you can expand as no. Okay, so after expanding this and grouping these two together, these two terms together, you can write the problem. Now, if you apply the arbitrary equation of the then Qi dot, then Qi dot, then Qi is equal to del del Qi. You can write Qi dot as del H del Pi. And since this is continuous and all, differential and all that, you can integrate the differential and you can write it, you can just write it this way. Now, del H del Qi is equal to Pi dot minus Pi dot. So this is minus del Pi. So Qi dot plus del Qi dot del Qi plus del Pi dot del Pi is equal. This term becomes 0. In this Qi and Pi are replaced by these del H del Pi and del H del Qi. And finally, the expression becomes this. Is this fine? Now, this is what is called a Poisson bracket, and we will not use it. This expression is called a Poisson bracket, and so finally you get this. So, any system like following the arbitrary equation of motion satisfies this equation. And if you want a system to be in equilibrium, then you would want the derivative to be 0. So basically, you would want your rho and the Poisson bracket to be 0. And this is identically true if rho is just a function of rho. So So if rho depends on PQ only through H, you can substitute here. So you substitute these here, you will get from 0 H times modular reference and this is this point. So when your rho is when your rho depends only on only through H, that time you can have a equilibrium system. Now we talk about something called the microcanonical dimension. So this is defined as a system where you have total number of states, total volume aspects, and total energy aspects. And I'll allow the energy to be within a range E and E plus 1. Because if you have any system, however close you make it, you can't like stop the interactions with the environment completely because there would be a vacuum and that vacuum also interacts with that comes to field theory or something, but the vacuum is not true vacuum. So a vacuum can interact with the system. So I'm restricting it to a very narrow range of energy defined by this delta. And so now we can define an accessible region of the phase space. And so by that I mean this volume. So this is the volume of the accessible region of the phase space. So here Hamiltonian of the system lies in this range. You will get over those only those values of C and G, and so that gives you the volume of the accessible region of the phase space. And so let us define these things. I did not define this. So this is like a thin shell, and this is a whole sphere in the basis of HPQ. I should not call it a sphere. This is the thin surface, and this is the volume. And if you see these two, you can write and let's define the density of states. Right. So this omega is actually is called the density of states. And it gives you the density of number of possible microstates with energy. So this is like either this delta you call it a density. And you can write omega E as then so this is like the surface of this volume, and this times delta is the times delta is the volume of the
one more question. When we are writing the Hamiltonian integral to energy, that is your regular physics conservation.
I'm not saying Hamiltonian is equivalent as energy. I'm saying that, so basically you have a microstate. To that microstate, you can assign a Hamiltonian in the function of that microstate. And then that Hamiltonian lies in this range of E and E plus delta. I'm saying only those states are active.
Okay. So when you say, but I don't think it is energy density can be conservation.
Yeah. Yeah, you can call it a conservative. So I just told that delta is 0, so nothing changes. And you can call it a yeah, this is what everything now from now is what it will be considered. So now there is an assumption and one more assumption required to write down the probability distribution in this system for each microstate. So that assumption is postulate of equal adaptability problem. So we have many states in this accessible region, and since this system is almost isolated and it is completely randomized because it's an equilibrium, it's kind of intuitive that no state in this system would be favored against the other state. So basically, the equal a priori probability postulate states that all the states corresponding in this accessible region have equal probability. And so the probability distribution is basically constant in the accessible region, and it is 0 outside the accessible region. So you can write down the probability distribution of this. And there is no proof of this as such, but it is intuitive, so we assume it is true. And then once we have the probability, we now define a quantity called entropy. So we define entropy as EB and this 1 by gamma is required to keep the normalization. And we call this gamma E as also as the microcanonical partition function. And this is an important information. This is how you define the entropy. And we define it this way because it has two properties. One is extensibility to do is it follows your how much time do I have? I mean, the next kind of derivation are kind of long, so
If you want to stop here, you can.
I can stop it. You guys want to stop?
If you want to go on a little bit further about it, you can go on.
No, but then I would need like at least half an hour. So I will, so next class I would start with showing how this function follows these two properties. And then see a theorem called Ensemble theorem. And then go to a different kind of ensemble. Before that, do some calculations, solve some, find the properties of some systems in this microcanonical ensemble, and then go to a different ensemble. Yeah. So, you understand this? That you define the microcanonical ensemble as something with constant simply and energy distance. Now, in your phase space, you would have many states which are in this range. And if you find the volume of the phase space where all the states inside that volume are in this range, that I have defined myself. And this is the volume such that your volume of all states such that x is less than. And this is like density of states. You divide this by this, and you call it this. Omega into delta. This delta.
It's called like the random imaging.
Okay, so gamma is the number of microstates on the system. Microstate that's equal to this. And in the system, for example, like you increase the number of microstates, and your S will increase. Now, once you're increasing the number of microstates, your system can approach many more states. So you're kind of increasing the number. I'll show that, but we have the second law, right? It states that entropy is an increasing function. So this function is such that it follows and it is extensive, which means that you take two systems. The total entropy of two systems will be the sum of them. That is what I'm trying to do. So I'm defining something called entropy. I'm showing that this reconciles the thermodynamic notion of entropy. So this is a very bridge from the microscopic state to the macroscopic state. Any more questions?
Guys, if there are no more questions, then let's end. Susmit,